Hi, here we've got a video on the Group 2 alkaline earth metals, and in this video we're going to concentrate on some trends in physical and chemical properties, and in another video we'll have a look at their reactions. So on the right you see the Group 2 metals: beryllium, magnesium, calcium, strontium, barium and radium. And there's actually quite a lot of magnesium and calcium in the Earth's crust. There's a fair bit of beryllium, strontium and barium, and there's virtually no radium. Radium's very reactive and also radioactive, and as a metal it's luminous and it's so reactive. Okay, here's what we're going to do in this video. We're going to have a look at the trend in atomic radius as we go down the group. We're going to have a look at the trend in first ionization energy, again as we go down the group, and the reactivity as we go down the group, and the melting point. That's what we're going to do. But first of all, let's have a quick look at the metals themselves. And here we have a picture of the metals themselves. Not that it's very interesting at the moment, but here we've got beryllium. We've got magnesium strip, we've got some calcium, and we've got some strontium and barium. We haven't got a picture of radium, but it looks pretty much the same. They all look fairly similar themselves actually anyway. And however, here we have a picture of this emerald crystal in its rock. So this is how we might find beryllium, as it happens in a compound in the Earth's crust. And beryllium's fairly rare. You would see beryllium at about 2 parts per million. 2 parts per million in the Earth's crust. And this is an emerald, and so this emerald here is actually a beryllium aluminium silicate, and its formula would be Be3Al2 SiO3, all in brackets 6. So quite a complicated structure. That is the structure of an emerald, which is where much of beryllium is found in the Earth's crust. And here we've got a crystal of barium. It's actually a barium sulfate with lots of impurities. And in the 1600s, this crystal was actually portrayed as the philosopher's stone, because you might see a glow, a green glow behind it, because when you shine ultraviolet light on it, afterwards the crystal continues to glow phosphorescently, and so somebody thought it might be the philosopher's stone, but didn't end up living any longer. Okay, that's a quick look at the metals. We can have just a quick look at magnesium as well. So magnesium, as you know from lessons, when it's burnt in oxygen in the air, it glows very white, doesn't it? And that's enabled it to be used as a flash for cameras for centuries. So there we have another use for a Group 2 metal. Now let's have a look at some trends. The first trend we're going to look at is that of atomic radius, and that increases down the group, as you might expect. So remember, atomic radius is the half the distance between two nuclei, adjacent nuclei. That's what's taken as the atomic radius. And as you go down the group, you see a chart like this on the right hand side, where, as you might expect, as you go down the group, you're adding a shell of electrons each time as you go down the group, because beryllium is in period 2, magnesium period 3, calcium 4, strontium 5, barium 6. All right, and so that's the number of shells that you have in each of those elements. And as you add the shells, you're obviously going to increase the size. And as well as increasing the number of shells as you go down the period, what also happens is you increase the shielding. So if you take this calcium, the full first shell and the full second shell and the full third shell offer shielding between the positive nucleus and the outer electrons. So as well as the outer shell being further away from the nucleus, it's also less strongly attracted to the nucleus because of that shielding, and so it can move slightly further away from the nucleus as well. So they're the two reasons why the size of the atoms increase as you go down the group. And the next trend we're going to have a look at is first ionization energy. And you remember that that's the energy required to remove the outermost electron from an atom. And we can see that that decreases down the group. Okay, let's have a look at the data. Here's the group going from beryllium, magnesium, calcium, strontium, barium. And you can see beryllium has got first ionization energy of 90. That decreases with magnesium to 738 and decreases and decreases until you get to barium, which is only 503 kilojoules per mole to remove that first outer electron. Okay, and with first ionization energies, we're looking at the same three factors. You're probably familiar with them. We want to have a look at distance from the nucleus, where greater distance from the nucleus means an electron is easier to remove because the attraction to the nucleus is going to be less. We have to consider the shielding by other inner electrons. Let's call it inner shells. And also the nuclear charge. Also the nuclear charge, where a greater nuclear charge, everything else being equal, will mean first ionization energy is going to be greater because there's stronger interaction between the stronger charge. Okay, so let's have a look at our diagrams. We've got our beryllium, magnesium and calcium atoms here again, and let's be clear about what we're talking about. The first ionization energy is the energy to remove one of the outer electrons. I could have picked the other outer electron, wouldn't have mattered. And for beryllium, we see that this is 900 kilojoules per mole. All right, whereas to extract a similar magnesium electron, and again, I could have taken either of the outer two electrons, is only 738 kilojoules per mole. And let's do the same for calcium. To remove that for calcium is 590 kilojoules per mole. Okay, so why does it get less as we go down the group? Well, let's consider our three things on the left. You can see for beryllium that the distance between the electron and the nucleus is smaller. Let's compare it directly to calcium, and that distance there of the electron from the calcium nucleus is greater. Okay, so the distance increases down the group, and what's more, if you compare the amount of shielding that this electron that's being removed has from the beryllium nucleus, it's just got one shell with two electrons in it, whereas with calcium we've got that same shell, but we've also got two more full shells of 8 electrons in them. Okay, these two here. So as you go down the group, the shielding is going to increase. As you go down the group, the shielding increases. However, the nuclear charge on calcium is greater. Calcium's got 20 protons in it, whereas beryllium's only got 4 protons in it. So we can say that the nuclear charge also increases. All right, but this has the opposite effect. This would otherwise make the electron more difficult to remove, therefore higher ionization energy. However, the effect of the distance and the shielding together is greater than the effect of the nuclear charge. Okay, so that explains the trend in first ionization energy. Hope that's been clear. Let's move on to another trend. The next trend we're going to look at is that of reactivity, and that increases down the group. And the trend in reactivity really is the inverse of the ionization energy trend. I'll explain why with this graph. So here on the bottom on the x-axis we've got the group 2 metals from beryllium, magnesium, calcium, strontium, barium as we go down the group, and the chart shows us how much energy is required to make a group 2 metal ion. Now when a group 2 metal makes an ion, it's going to make a 2+ ion because they've got 2 outer electrons. So for example, the electronic structure of beryllium is 1s2 2s2, and when it makes an ion, these are the 2 electrons that it makes, and that is going to give us a beryllium 2+ ion. The energy required to make that 2+ ion is what's in that column there. So first of all you have to atomize it, and then you have to take the first electron off, and then you have to take the second electron off, and then you have a gaseous 2+ ion that is there to react. I mean, for example, a beryllium 2+ gaseous ion is then able to react, for example, with an oxygen 2- gaseous ion to make beryllium oxide, like that. And so really what the reactivity depends on is how much energy is required to make that beryllium 2+ gaseous ion. And these are the 3 things that you have to these are the 3 types of energy you have to put in to make it into a 2+ ion. And you can see the red box is the atomization. The first ionization energy is the blue one, and the second ionization energy is the yellow one. And the second ionization energies trend follows the first ionization energy trend, same reasons. And when you combine all 3, you can see that for the same reasons, but in reverse, for the same reasons as with ionization energy, your beryllium is less reactive, and your magnesium is slightly more reactive, and as you go down the group, that continues until you get to barium, which is quite reactive. And the factors that we consider are the same. And let's just have a little tiny reminder of those factors. We've got distance of the 2 electrons that you're removing from the nucleus. You've got the shielding, and you've got the nuclear charge. Okay, so there's our trend in reactivity. Let's just illustrate it with a couple of pictures. Here's magnesium reacting with some dilute hydrochloric acid, I'd say, and you get some bubbles coming off there. Those bubbles will be hydrogen, if I've got the hydrochloric acid fact correct. Now, under the same conditions of temperature and concentration of acid and amount of metal, calcium, for example, would look more like this, where you've got a lot of frothing. It's not just fizzing; it's fully frothing up there because it's more reactive. A lot more hydrogen being given off per second than with magnesium. Okay, so hopefully that's illustrated and explained the trend in reactivity. Okay, the last trend we're going to have a look at is that of melting points, and they generally decrease down the group. Note that word generally. You'll see why when I show you the chart. So we're going to say that the melting points generally decrease down the group, with this exception of magnesium, and we'll say something about that exception as well. So firstly, let's consider why they decrease generally. Here's some calcium ions when they're in the metal, and to melt it we have to break the metallic bonds between the calcium ions. And let's just think about a metallic bond for a second. There's a repulsion between the positive nuclei, but then there is also an attraction between the electrons and the nuclei. like that. And the attraction between the electrons is greater than the repulsion between the nuclei, and that's why they're solid at room temperature, because that difference is quite significant, making the bond quite strong, and therefore that makes it a solid. Okay, but we've got a 2+ ion here for calcium, and all of the group 2 metals make 2+ ions in their metallic forms when they're solid metals. Let's have a look at strontium. Strontium, of course, is also a 2+ ion when it's a metal, but you can see the 2+ strontium ion is larger. You could just compare the size, and that's actually not to scale. It would be a bigger difference if we looked at it, but you can see the 2+ ion is larger than the calcium ion, for example, and a lot larger than beryllium and magnesium. And that is said to be the reason why the melting points decrease, because the distance between the metal ions is greater, meaning that the attraction between the metal ions and the delocalized electrons is less strong. Okay, so we can summarize that. The larger size leads to less attraction, right, and that leads to weaker bonds. And that leads to lower melting points. Okay, so that's the generally accepted explanation for that trend there. But in fact, it's not the only factor that determines the strength of the metallic bond. One of the other things that determines the strength of the metallic bond is the actual lattice structure. And when we look at beryllium and magnesium, for these melting points here and here, they have hexagonal close pack structures. So the structures of these ions when it's in a metal lattice is hexagonal, and you don't have to remember this. This is on top of the spec. So that's hexagonal close packed. That's what that particular structure is called for beryllium and magnesium. Hexagonal close packed. Whereas for calcium, strontium, and barium, their structure of the metallic lattice is called a cubic structure. These three are a cubic structure, and that's necessary because of the size of the metal ions is greater, and so they can't get into a hexagonal close packed lattice. They have to make do with a cubic structure. So the fact that sort of explains the anomaly of magnesium, which is hexagonal close packed, but it's not clear cut, as you can see. And I don't think you'll be, in fact I know you're not going to be asked to explain why magnesium is an anomaly. This last little bit is just for your interest. That just leaves us to finalize the video lesson by checking off that we've covered all of the things we wanted to. So we looked at the trend in atomic radius as you go down the group, and that increases because of the extra shells. The first ionization energy, that decreases. We went through the 3 reasons for that, which are the same 3 reasons in reverse, that reactivity also increases as you go down the group. And melting point, there's a sort of trend there. We can say it's a decreasing trend, with an exception for magnesium, generally because the metal ions are bigger as you go down the group, and therefore the delocalized electrons are more shielded from the positive nucleus, and that makes the attraction less, the bond less strong, and therefore the melting point less. Okay, so we have the melting point one done as well. Thanks, I hope that's been clear.